Thanks for coming for our fifth seminar for this semester. Our presenter today is Tad. Tad got his bachelor's in computer engineering and a certificate in nuclear engineering from University of Pittsburgh in 2009, and his master's in Virginia Tech with a degree in computer engineering in 2014. And he's now pursuing his PhD with Dr. Jeffrey Zavala research group. His research interests include cyber-physical systems, wireless communications, mobile computing, mobile security, context-aware computing, anything and everything.
Yeah, that pretty much sums it up for me. So let me just make sure my microphone's on before we start. I think it is. And so, all right, everyone, thanks for showing up today. D-Raj, thanks for the generous introduction. So I've got a question for you all, just a bit of a heads up. For a lot of, my talks, I like to have audience participation, so I will ask you questions. So question number one, and this isn't necessarily, or this isn't a test, but can anyone tell me what this thing here is? Light bulb, okay, so light bulb. You think there's anything else about this light bulb, anything that sort of stands out at all? Okay, so we got a funky looking filament. That's part of it. So the interesting part about this light bulb is that it's got a Zigbee radio inside, and essentially you can turn this on and off, adjust the brightness all wirelessly. And so why am I sort of bringing up like a wireless light bulb? When we, as wireless engineers, look at designs, we need, even though that we sort of try and encapsulate a lot of our designs in particular layers, so like the physical layer, media access layer, network layer. It's still, a good idea to understand what are the applications going to be? What's the application layer going to be sending to us? So for the application here, it's going to be very basic. You're probably going to have more data coming from this light bulb than you're going to have data going to it, because you need like one bit to turn it on and off, and maybe a couple bits here and there to change the brightness. And so let's sort of take a look at LTE. So I sort of whited out some of the lower columns, but so what? Is there anything that just stands out to anybody right now based on the way that the LTE uplink and downlink are set up? Exactly. Yeah. So the observation here is that if you essentially take a look at the downlink, you'll notice that, for example, in almost every example, the downlink is about half of the uplink. And so, the typical LTE application, when you look at that, is, let's say that we want to, request this, just a video, something to watch, like during the seminar. Typically that request will be on the order of kilobytes, right? A couple K here or there. And then the video response is going to be just much, much larger coming back, and that's going to be in the order of gigabytes. And so if we look at sort of the architecture of communication systems, some systems like LTE do take this asymmetric traffic into account. And what I'd like to do today is take a moment to talk about some research that has wireless implications. So as wireless engineers, a lot of devices like that light bulb, everyday things are now sort of sending data, whether it's 1 bit, 2 bits, 3 bits, kilobytes worth of data or gigabytes worth of data. And specifically, I'm going to talk about wireless devices as industrial control systems. So a little bit of a background. So a little show of hands. How many folks have heard of an industrial control system before? Anybody? Okay, a couple people, not that many. So industrial control systems are, for example, used if you go down to the edge of town in Blacksburg. Industrial control systems control the water treatment plant. So they use ICSs to clean up the water, filter it, and then send it back to you. Other industrial control systems are probably in some of the newer buildings, like the new engineering building. You'll notice that they have like a really fancy like control panel over here, and you can turn the lights on and off. You can dim the lights. You can control the projector. Those are all sort of industrial control systems as well, just not they're not necessarily considered like critical infrastructure like a water treatment plant would be. But one of the interesting things about industrial control systems is you can have lots of little devices over a huge area that have to essentially work in harmony. And so what I'm here to talk today about is not the wireless aspect, but I'm going to provide a little bit background from the programming aspect. How do we create these applications? What's important about the applications? And help provide some insights so as wireless developers we can sort of figure out, okay, what type of uplink should we have? What type of downlink should we have? And possibly maybe motivate some future research. So going back to the example, almost everything these days is controlled through an industrial control system. The solar panels on the car park, right behind us. The heating and cooling systems are largely now controlled by computers. So it's not a mechanical control system anymore. Smoke detectors, they're in new smoke detectors will actually communicate wirelessly. So when one smoke detector goes off, they all go off in your entire house, and they're very, very annoying, which is sort of the point. So going back, light bulbs are getting smarter. There are no sprinklers in this building, which is probably bad, but a lot of sprinkler systems are now going to be controlled as an industrial control systems, and even the lifts, the elevators. And so all of these devices, they form a industrial control systems themselves, but they're really becoming very ubiquitous in our lives. It's almost many devices are being converted from like static devices to the proverbial smart device. And so these sort of items are everywhere. And at the end of the day, if you can see sort of the firefighters down here, at the end of the day, someone has to maintain this. So from a wireless perspective, that's a bit easier because we don't have to worry about the maintenance. But from the application perspective, that is, well, it can be very difficult. Another challenge, or should I say the first challenge looking at industrial control systems is a lot of times they're deployed in very remote areas, and sometimes those areas are also very electrically noisy. So, for example, oil rig, there's sort of your middle of nowhere in the ocean example, where wireless might be at a premium because you're using a satellite link. And another example, this is meant to be a printing press. And so there's lots of electric motors generating noise that can interfere with wireless signals. And so one thing we want to look at when doing industrial control systems applications, we're going to have a probably tightly constrained link as far as how much bandwidth we have to play with in some of these environments. So that's sort of challenge number one, is the environment itself is going to limit how much bandwidth you can get across the link. Challenge two, this is a bit of a softer challenge, a little bit less wireless related, but so this is sort of an example of a typical industrial control cabinet. There's a whole bunch of electronics in there. Any guesses? Can anyone sort of point out to me, like in this picture, so top, bottom, left, or right, where do you think the actual compute hardware is? Where do you think is the industrial control system in this example? Yes. All right. So those sort of blue cards right there is actual PLC, and everything else in the box is sort of, it's part of the system, but not necessarily a compute or an intelligent part of the system. And so one of the tough parts of provisioning and maintaining these applications is you walk up to a cabinet and you think to yourself, okay, what application am I supposed to use with this? At the same time, some of those applications, PLCs, aren't as elegant from a programming standpoint as, let's say, some of the apps you write maybe in MATLAB. PLCs, they'll write directly to memory. So if you were to, let's say, load the wrong application, for example, you could be writing to memory locations and you can be putting the PLC into a state where you can't recover because you're writing directly to a memory register and you're writing just the wrong value. And so that's some of the difficulties as figuring, okay, HMI is the term that's used in the industry. It means human-machine interface. It's essentially a very application-specific term for a GUI. But how do you find the right application that interfaces with this machine when you could probably walk into a factory and you have rows and rows and rows of these machines? Challenge 3 is also evolution of the application. So Challenge 3 focuses around typically when you, let's say, update your business logic. Let's say that you upgrade a piece of hardware. You essentially need to update your logic to reflect that, okay, this ICS system is now interfacing with something new. Similarly, you also need to update the HMI as well, or you need to update your GUI or the application that you use to interface with your industrial control system. And so this is sort of more of a software challenge, not necessarily a wireless challenge. But in this case, I want to sort of highlight the process. So a lot of times with industrial control systems, you'll have, for example, factory managers, you'll have factory workers, and they won't do the updates themselves. Instead, they are tasked with maintaining the production line, keeping things going on the ground. Many times, you'll sort of have a PLC vendor who is contracted. They'll actually send out technicians to maintain the equipment. And what makes this a bit unique and interesting is you have someone walking into this factory that doesn't really know, they know who their point of contact is, but they don't also know, for example, okay, I just updated this PLC. Who else uses this device that I need to inform that something has changed or something is new or something has been updated? And a lot of times the updates just, all right, so another pop quiz. How many folks have an Apple phone? Okay, a couple. How many folks have an Android phone? All right, anybody still have a flip phone? Anybody? Oh, okay. So just like Apple and Google, a lot of times they will have a development team off, somewhere who actually develops the updates, and technicians, who would be all of you in this case, update your phones. And so that's more of a software as well as an interpersonal challenge, but it's something to be aware of that, when you update one piece of software in an industrial control system, you also have to update both the HMI, and you need to go reach out to, the human aspect and say, hey, I finished this. Please notify whoever uses this machinery that X has changed, or we put this fancy new emergency stop button in, and this is how it works. So now let's talk about something nerdy, specifically no effort rapid development, which is sort of the name of the framework that me and my colleagues sort of proposed to address some of these challenges. So for challenges, I think the most salient challenge for wireless is going to be looking at DSLs. So DSL is a domain-specific language, and also looking at the mobile cloud services aspect. So how essentially do we create the wireless systems that can support these applications? So going back to the light bulb example, you control that light bulb with 1 or 2 bits of information. But at the same time, that light bulb might be able to send a couple of things. You could probably put a temperature sensor in there, so you could use it as a remote thermometer, or you could use it as a remote sensing platform in general. And so what's sort of interesting here is that in the ICS sense, and going up a level further to the general Internet of Things, a lot of the devices are going to sort of flip the traditional norm. So LTE, you have a very robust and high bandwidth downlink. The uplink is also from the, let's see if I can go back a couple slides. So going back to, typically the uplink was about half the throughput of the downlink. Now in this case, there are technical challenges because of that. For example, doing the OFDM on a downlink is a bit easier because of some of the assumptions you can make at your base station. But it's also because the use case that drives that, most of your uplink requests are going to be, much smaller compared to your downlink requests. And some of the upcoming technologies might flip that around, where your uplink now has to be double the size of the downlink because you're sending one bit to turn something on and off, and you're getting back let's say 10 times as many bits from a heart rate monitor or a temperature sensor or sort of any other IoT device that's out there. And so taking sort of a look at where the software, where the application layer is going, can sort of give us insights as wireless engineers as to, okay, at the lower layers, at the network layer, at the media access layer, at the physical layer, what changes do we think we need to make to be able to support these applications? So another buzzword question. How many folks have heard about what the cloud is? This is probably a bit of a dumb question, but okay. Okay, a couple people. How many folks do you use the cloud at all? Yes, no? Dropbox? Yes, exactly. One of the things that everything is moving into the cloud these days. The cloud is just essentially saying, okay, we're going to put all our compute resources in 2 places on the continent, and then we're going to route your traffic there. And industrial control systems are also going to sort of move in that direction as well. So in this case, what flew over was a little QR code. For NERD, one of the challenges, I think it was challenge number 2. When you look at a PLC, what application should I load? I don't know. A lot of PLCs will have something like a device marker on there. Something where a technician can go up and scan and say, I'm looking at the following PLC. For NERD specifically, we envision being entire applications on a QR code. So you can walk up to a PLC and you can essentially download all the information you need just to interact with that device. So our technician comes over here, they come and they read that barcode, and in this example is a QR code, but from a wireless perspective, this could also be NFC. This could be a very short-range communications method that can, sustain a certain bandwidth. But in this case, once you read the QR code, you can essentially provision the device. And one of the other really useful things is that, going back to challenge 3, what happens when someone updates this device and I walk up to it? I don't know it's updated. In this case, you can essentially use cloud services to say, okay, you downloaded version 0.1 and we're on version 2.0 right now. And instead of getting the application, you can then reach into the cloud and say, give me the latest and greatest, so that I don't essentially use some outdated application that could cause disastrous results with the PLC. And with the cloud aspect, you can also, for example, have the cloud do translations between, okay, you essentially issued a command from your tablet, and whatever that command is can be translated into something the PLC understands in the cloud, as well as providing additional compute resources and doing verification and validations. And, are you supposed to be accessing this PLC? Are you sort of the right person? But this is sort of the discovery and provisioning model that we see industrial control systems, but in general, different smart applications moving towards. So let's talk about that application. So when you think of an application, what do you think is in an application, like when you download it from an app store? And you would just shout it out. What do you think is included in applications? hopefully some code, because I mean, okay, how many of you work on code for your projects in wireless? Okay, all right, so there's some code in there. Other things that applications include are assets. So assets are, for example, all those great images. So let's say that you use Google Mail, right? You know, the send button, the big red button that says send. That's actually, in many applications, icons are stored in the application, and when you have to download that, that can be much larger than the actual code base is. The other really important observation is that applications include links to data, and the data is the most useful part. So for example, let's say that you're using the Yelp app. Yelp knows two things. It knows, one, what server it wants to talk to, and two, it also knows how to talk to that server. So let's say that someone's asking for, hey, what's a great place to go, you know, for a technical meeting, you know, so you can sort of put that into Yelp, and Yelp will say, oh, we're in Blacksburg, you know what's really nearby? PK's. It essentially knows how to send that data and interpret that data back. And so as part of NERD, we essentially created a domain-specific language that attempts to separate out your data streams from your assets. So for example, if we go through the slide, one of the big things you'll notice right here is, you know, what data as a technician should I show? And a lot of types of data conform to particular templates. I mean, as engineers, how many folks here have never used, well, I won't try that, but how many folks have used a bar graph or a pie chart or something? You know, you sort of know how you want to visualize your data. And so that can essentially be put into, you know, sort of a common component framework. So let's say you want a scatter plot, right? You don't need to essentially define that scatter plot from scratch. You can just say, okay, I want a scatter plot. Now, scatter plots follow a particular pattern, right? And that pattern being, what data should I show? Where should I show that? So let me see if I can scribble on this a little bit. But out of curiosity, can anyone like read this text at all? A little bit, yes, no? Okay. So up here, you know, it says title, target URL, you know, X label, Y label, because as engineers, we should always label our axes. But most importantly is that when you start looking at the series, okay, where do we get our information from, right? This is probably more important than, you know, visualizing some of the information is where do we get it from? How is this information applicable? And so with the DSL, we can essentially say, I don't need to write this application from scratch. I just need to say, which pattern am I going to use? And how am I going to, where should I get that relevant data from? And a lot of applications are really, you know, requesting large amounts of data. Going on, so like I said, these are all components. So you can compose these. So you can take a bunch of scatter plots. In this example, we're actually showing from way back when this is sort of an RSS reader that we did in a prototype we created, where we have this domain-specific language, and the domain-specific language, come on, is just this entire screen right here is composed mostly of where do I get the data from, as opposed to how do I draw the data or even the data itself. And so you can essentially separate that from your applications, put that on something as small as a QR code, or use something like NFC, and you can essentially deliver that wirelessly to your device. And you know, so this is one possible direction that wireless applications could take, where they're going to essentially depend on the network to provide everything else, provide all the data. You can even separate the assets such that you can download these assets along with your actual data streams. And so that's sort of one vision of, you know, the potential future of what types of wireless applications are going to be out there, and how will the lower layers of the OSI model sort of adapt and evolve to meet some of these new applications in the same way that, you know, LTE has sort of evolved its asymmetric uplink and downlink since most data requests on the uplink are going to be small, and most of the responses coming back are going to be, orders of magnitude larger. So just to quick overview. So we also looked at NERD and we also looked at the usability. So this is more from like a software standpoint. So why would anybody ever want to use this when I can go to the to Google Play or to the Amazon App Market? And so part of this is because when you look at all these PLCs, you might not know, for example, okay, these applications all look the same to me. But so what we did for the trial is we sort of broke it out. So all of the blue graphs are going to be starting, for example, our NERD application. So that you start the NERD application, and then it can go grab that application for you. Come on. Technology never works when you want it to. With NERD, because we were using QR codes, so the red bar is typically step 2, which is, okay, go and scan that device marker, go read the domain-specific language, and go fetch the data and actually build the application on the device. And step 3 is typically load and instantiate the app. And we tried for most of these trials to keep the categories as similar as possible. So pretty much all of the trials that, all of the trials, so these trials down here are all going to be, these are the NERD trials. So this is sort of the experimental data. What we did was we compared NERD to going to a regular app store. So, surfing over to Google Play and sort of this method 3 is imagine you click a link to a Google Play app and it loads that app for you in the App Store. At the top, method 4, what we do is we looked at a very typical use case. So I want to go search for some apps. I know the name of the app I'm looking for. Let me go actually, go to the search bar, type it in, we'll go through the search results, find the app I want, and install it. So moving along. So like I said, we have some typing exercises as part of using Google Play. You also have going through, your search results, loading the app description once the store has found the application that you're looking for. This step here is also pretty important, especially in Android. This is something we do implicitly on other platforms, but it's looking at the app permissions. And like I said, from a software standpoint, for each of the Google Play apps, you go and you have to manually say, okay, I allow this app, my camera, and it can write, and it can, record. In this case, you'll notice that there's no explicit permissions check in NERD, and that's mainly because NERD inherits the permissions when you first install it. So when you install the NERD app, any apps that run inside of it essentially have the permissions that it was given when it was initially installed. And finally, you have downloading the app from the cloud. So a couple notes about NERD. So method 1, what we do is we put the entire DSL onto a QR code. And that made QR codes huge. Like a very simple application could take something around 1,600 characters, and that's a pretty big QR code. An application of that size will look something like this. So this is sort of, I sort of shrank the text down a lot. And if you do the same thing with a link instead, it's much smaller. But that's some of the reasons that for the first trial, you'll notice that scanning the application when the entire application is stored on a QR code or on your marker takes, that red bar is much bigger than the method 2 red bar. Now the fastest method from Nerd is a method 2, and what we did was we put a link to that application. So that was meant to simulate, okay, let's imagine that our application was provisioned and we had to go get a new application because whatever was on that QR code was out of date. So this is actually a device reaching out across the network or possibly even across the internet and downloading the latest version of the app and loading it from the that smaller QR code was actually a lot faster because there was less complexity in the QR code. It was a smaller QR code. And so on average, we found that using the Nerd methodology to provision an application was about 1.4 times quicker than scanning the entire application from a big barcode, and about twice as fast as loading it from a URL. So imagine just clicking a link and having your web browser go to the App Store for whatever platform you use. And we found it was about 3 times faster than having to do a manual search. So opening your phone, typing everything in, going through the list. This can also sort of reduce frustration, especially when you're staring at all these cabinets that look exactly the same. If you can just pull that app that you're interested in. If we look at provisioning from a traditional app store, a lot of the provisioning added additional steps. So, for example, does everyone understand permissions on their phone? It's some people may not, and so they stop, they look at the permissions, they decide, okay, should this app have these permissions? Maybe, maybe not. And finally, method 4, which was just a manual search. So what I compared this against was searching the App Store and installing a Blacksburg Transit app. We were able to build a Nerd app that mimicked the Blacksburg Transit app, and so that's sort of what we compared against. But we actually found that the manual search was fairly error-prone, so having to type things in when you're looking for apps can slow you down significantly. Whereas if you just, for example, if I were to just walk up to this AV unit here, and if I could scan a device marker on that AV unit, it's probably going to be a lot easier as opposed to following instructions that say, okay, go here, open this app, or download this app from the App Store, and then you have to do the rest of the provisioning process. Now, like I said, this is research. We made a lot of we used a lot of idealized cases, and certain assumptions were made. So the picture on the right, this is what a typical HMI looks like in a industrial control system. I think this is I got this from another journal, and this was a case study taken from a steel manufacturing company. So typically these HMI applications and industrial control system applications are fairly complex. And everything I presented in Nerd is, we have these simple widgets. You can do a pie chart. You can do a scatter plot. You can, make a list. And, the big question being, can we essentially create a template for all of these, standard cases such that as an app developer or as someone who works with these systems, you can use this domain-specific language and you don't have to specify everything from scratch. The benefit of the domain-specific language is you can take that, you can take a pattern, so something like I want to draw a bar graph, and what you can do is you can say, okay, typically a bar graph has these following features, so just tell me where to get my data from. And so this is sort of one vision, but definitely additional work would need to be done to really make this let's say a complete drop-in solution for current software development. So to conclude, Nerd is one possible way that you can essentially do flexible provisioning of your applications as well as complete them in the life cycle. So as wireless engineers, why is this important to us? Why is going over software patterns and how applications are provisioned? And for me, it's because a lot of our work looks at, wireless links. What type of data is going to be transmitted? How much data? How often? What latency do we need to achieve? And so this sort of is one research project that looked at what's the next generation of the applications going to be. And so for wireless folks, question for us becomes, all right, so if this is one potential way or one potential research look at future applications, how does that impact us? Will current communication systems be able to scale effectively if, almost as industrial control systems become more complex, or as, IoT-style devices become more, embedded in our environment? Will LTE be able to keep if, suddenly every light bulb in, let's say, this building is able to talk over LTE and be controlled? It's sort of some food for thought. So thank you all for, coming. And so any questions about wireless, about nerd stuff, about applications in general? Yes. So NERD was a project, so it was originally called Smart DNA, and it was a project sponsored by Siemens, and Siemens actually came up and said, let's call that no effort rapid development, because some of the challenges they have are when they go out into the field, they have to go update apps, let's say when they install new hardware, and so how can we essentially support our developers out there who are, they could be in, let's say at an oil field in Texas in the desert, or they could be, right down at a, let's say the VT power plant where I'm sure there's a lot of electrical noise and they can't necessarily, do lots of quick, or they can't do big uploads and downloads. But yeah, that was, I believe that was Mike. Let me go back to the first slide. I believe Sean, who is our collaborator at Siemens, was one of the guys that suggested that name. No, so a lot of our work happens more closely at sort of on mobile devices, but that doesn't mean that you couldn't do this with MATLAB. I'm sure you could write an interpreter in MATLAB, or you could even write an application that could interface with MATLAB and feed MATLAB data. So, all right, well, come on, technology. There we go. Thank you so much. Yeah, no, this just takes you to the website. So this was done as part of the Magnum Research Lab. The Magnum Lab ended up moving to Vanderbilt University. So hopefully that website's still up to date, but there's still lots of cool research going on.